Today we're not gonna do coding. Uh, I have the feeling I'd like to explore a bit sort of entanglement in the direction of whether there's a way we can characterize entanglement at the register level, for example, kind of try to go one level up, right? Because so one of the things that I've been thinking about recently is the fact that in the whole EHS story, we keep talking about qubits, right? So we have, Q0, Q1, and then if we apply a Hadamard gate, like so they are in the zero state initially, right? So that's the initial state. If we apply a Hadamard gate, then they end up in the 0+1 state, in the 0+1 state, and then or yeah, or let's say this is in the one state, doesn't matter, and this is 0 - 1 state, and now you apply a control. So this is Hadamard. Now you apply control X gate, and so what you have is a system that is like in the 0, 0 - 1, and in the 1, 1 - 0, basically. And here's where you see phase kickback, right? So you have, well, because basically these two states are the same up to a global phase, which is -1. And so you end up with like 0, 0 - 1, and -1, 0 - 1, which in turn takes you to the state minus minus. Yeah, let me just double check. So if this is in the one state and we apply two Hadamard gates and then a control Z, control X, then we are in the minus minus state and it's not entangled. So this is phase kickback, and it's relatively easy and simple to see with an entanglement hypergraph why this happens, right? It's because there's this sometimes operations, and maybe I can say this happens. It doesn't necessarily have to happen in superposition, actually, no. I don't know, but it happens because there's these operations where, the operation basically like it's not that it adds a global phase and that global phase is kicked back, because that's not always the case. If I would do another, if I would apply another operation that is not a control X that also adds a global phase, that would not necessarily mean that it gets kicked back. It gets kicked back because the overall effect on the target qubit is that it does not create entanglement. So at least this is one of the extreme cases. Like, I have no idea how this would look like partial entanglement, right? I guess if we don't, I guess, yeah, I mean, I guess if it's not an X gate, I guess if it's like a quarter of an X gate, you also get a phase kickback, right? Exactly. You also get a phase kickback because, yeah, yeah. You see, that stays in. That's funny. That stays in the minus state. That is actually really funny because you'd think, that it would just rotate to something that is not really minus, right? Oh wow, that is. So if I yeah, so literally this is just like just the phase kickback. Yeah, but it's interesting because I would have intuitively thought that like if we are, so let's get rid of maybe this part here and let's go. So if we're So let's get also rid of these here, rid of these here. So if we're at this stage, and now I apply a CX quarter, actually that goes away as well, right? Like the zero component does not touch the state. Now the that's interesting because you now say, okay, so the one, and now you have the minus state, right? And then and you want to apply. So let's see how this looks like. So if I open Quirk again, I have a quick shortcut here. If I have the minus state and I apply the quarter, yeah, nothing happens basically, right? Well, it adds just a phase, like a global phase. Essentially, yeah, of course, because what it does is it kind of it adds the same amount of shift to the zero than to the one, right? So you can think of it without going into the matrix and what it does, right? If it's let's say it turns a quarter of his, I'm just making it up, right? Let's say it takes a quarter of the zero and turns it into a one. So you have like, so you've got like, you've got like 0.5 of zero, and these are, I'm just making up these numbers, just probabilities, I guess, and 0.5 of one. So it basically, it kind of, yeah, intuitively, it just takes a like a quarter, and for the sake of like, this can just be really any, like, actually, let's make it generic. So this can be really any fraction, right, or any exponent. I don't know, alpha. That's probably the wrong thing to do, but like, where alpha, so alpha is between kind of, yeah, 0 and 1, right? So like I'm just interested in the case of this being a fraction, but I mean, I think for bigger exponents the same would apply. I mean, then you're just applying the same operation multiple times, so because it's, yeah. But so if you do these, I guess what happens is that, say, a portion of these stays. So it's like you end up with kind of like what, 0.5, like something like these being of 0, right? And something like these of 1, and that kind of comes from the 0 component. And the same happens here, right? So 0.5 of 1, right? And 0.5 alpha of 0. That comes from here, right? Now, these things should, yeah, if you add them together, right? So these would go with this one here. So you factor the 0.5 out, and then basically the alphas cancel out. So you're back at your 0, 0, 1. Now, if this is a phase of -1, right? What this means is that now the so the 0 component is the 0. No, so from the 0 component, right? the stuff that we move to 1 is positive. The stuff that we move to, no, what am I doing? Um, it's almost like the sign stays there, actually. I mean, the sign, it's just a relationship between the two, right? So we can ignore the sign and just plug it in at the end by, yeah, I mean, you end up with a 1 minus 0, so it doesn't really matter. And that was probably too much of a convoluted way of saying that these things don't matter. But the interesting thing is that the the phase, right, is -1. Well, it matters because it's not going to be -1. No, that's wrong. So the 0, right, part that we take to be 1 stays positive, stays negative. No, positive. And so that stays positive, and those stay negative exactly. So those two guys stay negative somehow. I don't know if I can do that. -0. Exactly. But how do you compute then the actual difference? I wanted to see. I think it's because so there should be a minus in here for sure. I'm not sure how to get that relative phase, which is funny because it's kind of really telling me that I got it a bit wrong, I think, when sorry, when I sort of talk about, this being 1 minus 0 and then factoring out the minus, and yeah, but that's really, so the portion of 1 that goes to 0 has a minus. The portion of 1 that stays in 1 has a minus. The portion of 0, right, because we're coming from this state, the portion of 0 that stays 0, they both stay positive. So okay, so what I don't know if you can do that though, that the minus is taken with the 0.5 alpha, because then you would say the 0 part is, you know, 0.5 minus 0.5 alpha, minus 0.5 alpha, right? Yeah, so basically 0.5 1 minus 2 alpha, correct? Is that correct? yeah, because we factored the 0.5, and so it's 1 minus alpha. And for the 1 component, we have 0.5 alpha, and then we have 0.5, then we have minus 0.5, and plus 0.5 minus 0.5, so minus 0.5 plus 0.5 alpha. So we kind of basically have minus 1 or minus 0.5, right? 1 plus 2 alpha, so to say. So yeah, but these things, I mean, don't really tell me anything about the relative phase being a quarter or something. 0.5, because I'm maybe it's because it started off with just probabilities and I should have, yeah, that's not the good way of reasoning about it. I should start with the amplitudes, and then I would probably get that. And you know, kind of what it probably means to rotate that by alpha, not like just adding that. I was just trying to reason that a whatever portion of knot you do classically, like it leaves you in the same state. So I think that was useless. But anyway, so in these cases you have a the phase kickback. That's what I was going to. So we have this phase kickback, right, that we can see here happening dynamically. But this is because we have this very, very specific operation, a control knot, like which is just like an XOR, right? But it's if you one thing that I've realized recently is when I was exploring some of the algorithms that Craig has here, right? And I often see him do that. I see him do something like this, like go ahead and to entangle for example, two registers, right, of 2 qubits each. He goes ahead and does something like, that's input A, and we're going to use the addition gate, right? And now you have everything entangled. So the way that you can see or you can read these, right, is if you think of it as like you have to actually put a bit of effort and just go away from the qubits, right? And think that in the, so you have two registers, right? So you have two registers. So one is, whatever, right? And so the first register is actually 2 qubits. So you can represent 4 numbers like unsigned. So 0, 1, 2, 3, 4. So the first Hadamard layer puts that into superposition of like 1 plus 2 plus 3 plus 4, right? That's kind of, if you would translate the binary strings, that's what you could interpret the register to be in. And what this operation is doing is, what you're doing is you're saying, take each of these elements of the superposition and add them here, right? So essentially, and this is in the 0 state, and actually this is wrong, by the way. This is really wrong. This is 0 plus 1 plus 2 plus 3. And so what this operation is doing is it's entangling both registers in a way that you have the states like 0, 0, uh, uh, 1, 1, and I'm on purpose using the comma to distinguish the registers, right? 2, 2, and 3, 3. So that's a superposition that you have, right? And you can see it here actually, yeah. So this means that, like, I mean, at least that's the way this is built into Quirk, right? Now, I'm kind of, I'm feeling like there's a some important intuitive step that one has to do here to try to think properly about entanglement, because now you're kind of crossing a bit of a barrier where you're not talking about qubits anymore, right? So you're kind of back to your to sort of I'd like to think about the register as a system, right? As a subsystem, not necessarily the qubits. Maybe that's what I should think about, and how are these entangled? Because to be honest, I think the the entanglement hypergraph could be used at that level as well. Let's say that instead of, we in so instead of using the qubits, I would say that we have a register nodes. Yeah, nodes. So the first register node starts off in the 0 state, and the second also in the 0 state. After the first Hadamard gate, right, we get into the state that is like basically 0 plus 1 plus 2 plus 3. I mean, that is like, here we have to sort of treat these as a qubit, not a qubit anymore, right? So kind of the Hadamard equivalent would turn you into these, which is sort of, it's sort of a plus state for like a 4 levels qubit, right? I don't know. You could think about this way. I guess, each qubit has or each starting to lag again. So if I start off, if I Hadamard the 1, then I get the 0 minus 1, 2 minus 3. That's it, it's like, you know what I mean, right? So I mean, you're not like, this is nothing new. It's just you're reading the, if you would have the 1 state and you would take this kind of Hadamard on this qubit, then you go into the 0 minus 1 plus 2 minus 3 state. Because remember, these sign patterns are important because this is what makes the whole operation uncomputable and reversible. So you know where you come from, right? But then how do you characterize now, like, these entanglement, right? So the plus A operation has done these. So what these, it's not a control node. We're not talking about controls anymore. We're talking about like input and output relationships somehow. So, and I guess one could think of this input and output always splitting these sort of unconsciously, right? And saying, look, now I'm going to have 4 branches: the branch 0, 0, the branch 1, 1, the branch 2, 2, and the branch 3, 3, right? And I think that could work, because what I'm trying to get to is, how does phase kickback? How does one think about phase kickback at this level? But it seems like it should be the same. Like what what intrigues me the most is this. So if I clear this circuit and open Shor's period finding, right? It's like I'd like to be able to understand um, the fact that in here you have exactly this pattern, right? I find this is it's beautiful you can implement these things in Quirk like these. So forget about these boxes, but you set your register to 1, and then literally like because you see here that you're kind of hiding all the complexities of doing qubit-wise operations. You're just saying take that and take that A and treat it as the exponent of these. And so like it just opens a completely different way to explain that. Because usually you're like, yeah, you do controlled modular exponentiation, and then you have to understand that there's some sort of phase kickback in there. But for me, it's like, how? Like, I can't explain myself well enough. The point is, this phase kickback, it's not something that you've engineered there, right? It's just there as a result of applying this operation. And it's telling you something about this operation, which is not, at least to me, yeah, it's got to do with the cycles, I guess, with the modularity. But I find this really neat that you can just, you know, this is beautiful. You can just, you're just saying, just take that as the exponent. Um, this is your guess from the algorithm. So this is 26. This is your module like 55, right? So mod 55. And kind of you're just multiplying the whole register, which is at in the 1 state with that. And like you don't care anymore about the qubit level entanglement, I guess. That's what I want to be able to do, is like we understand entanglement between qubits, but like how can we move to registers, right? And at the end of the day, I kind of realized that, well, then you just need to move to a qubit model to understand these. And so what I want to is like I'd like to see with an entanglement hypergraph, how can how can we how can we model these phase kickback? That is what then the the QFT reads back. And what does it mean to apply QFT into a register like these? Well, it means QFT in each of the elements, right? That's the I like that. So I like the fact that there's this just mental step that you can do where you're like, well, you just need to move to a QDIT model. Is QDIT the right? I think QDIT is the right. It just means like a qubit that it's not. It's a higher dimensional. Yeah, yeah. A quantum D. The unit of quantum information describes the instance of these states. Yeah, so it's 2 states, it's qubit. Yeah. So I wonder how. Okay, so we consider the separability of various joint states of d-dimensional quantum systems we call qubits. We derive 2 main results. The separability condition for 2 qubit state that is a mixture of maximally mixed states and a maximally entangled state. Lower and upper bounds on the size of a neighborhood. Okay. I don't I don't think that's what I'm looking for though. Operator representation of qubit states. Maximally entangled states. No, that's not what I want. Qubits and qubits. I mean, it's just one more level of abstraction. It's just that your typical editor doesn't help you anymore, right? At least to study this entanglement. So now I can talk about the actual register being entangled, the actual registers being entangled, and sort of what are the values that correlate. And those are, you can farther unpack that and then see that it's see that in reality, for example, this branch here, right, is like a 4-qubit branch that is like 0, 1. So that is the actual branch. It's just that we know that we make a split here. Yeah. And like you can have, I guess, yeah, you can have like branches that look like these, right? Or like -2 or whatever. So this minus is then just because you're not saying that the 2 is negative. You're saying that the 2 has a negative phase. It's a bit different, right? So here, when you start dealing with numbers, it can be a bit tricky just not to get lost with these. So, okay, but now how do we study phase kickback with these, right? Like here there's an obvious phase kickback. Yeah, I mean, here there's an obvious phase kickback. It's just gonna break. Because or not, like because if I okay, so what happens if I do this now here, for example, right? It's an equal thing because we have basically a superposition of 0, 1, 2, and 3. Not a superposition, but a mixture. So what this QFT does is it would do the QFT for 3, the QFT for 2, the QFT for 1, the QFT for 0. And kind of give you something that it's, that is all mixed up, but that does not, it doesn't change the, but if this is the multiplication, now we're talking about something happening here, right? Now the multiplication is a bit more, is a bit trickier because the multiplication, it says it's no effect if the input is even. That would be irreversible. So that's the reason why you have, these here. Does this mean that Shor's algorithm works only because multiplication can be irreversible? Hmm. Because the thing is, I don't think you're kicking off. I'm having a weird feeling. Like I'm not so sure if you're kicking off any phase kickback. Well, you should, right? Maybe that's what you're doing with the states where this would be irreversible somehow. Like let's uh, let's do that, right? So let's say you have, because with the multiplication is more interesting. So the way I would go about these, right, is you have so you have the 0 and 1. Then you can have the 0 plus 1 plus 2 plus 3, right? And then the 1. And so you probably basically end up with, in theory, 0, 1. No, 0, 0, right? But it's even, so it stays as 1. Then 1, 1, 1. Then 2, 2, but it's even, so it stays at 1. Um, and 3 times 1 is 3. So we have basically, but that's what I don't get, is that in theory, input register, the input register is really just like that, right? So okay, there's something off with the way that I intuitively think about this, because it should be a total equal probability. And it's obviously not, because it says it doesn't have any effect. I mean, let's see, if I say 0, 1, and I want to take a look at the chance display here, I get a 1. If this is 0, I get a 1. So that's correct. So if it's a 0, it's a 1, it's correct. If it's a 1, 1, it's correct. If it's 2, it's a 1. So I'm so that's correct. I mean, okay. And if it's 3, then it's a 3. Okay. Hmm. But let's take a look at the phases here, if possible. So I'm gonna take an amplitude display, and I'm gonna start by saying, what if it's, yeah, the thing is, if it's 0, it's non-existent. If it's a 1, then we have, it's either 0, 1, 2, but they all have, like, there's no relative phase in here. All the relative phases are okay, and if I just change with the 3, it's also all chill. So how can we be reading anything with a QFT? Well, yes, because what you're reading, because that's my point. It's like what you're And maybe this is something with the modular exponentiation. Maybe it's pointless that I'm trying this one with multiplication. But it's still, what you're reading is a sort of an aggregated, like a superposition of all these different QFTs that you're doing on the node here, right? So if I clear these and I do, okay, so the inverse of these takes me to the equal superposition. The inverse of 1 takes me to these, right? Oh, so actually, cool. So the QFT inverse to 0, 0 takes me basically to the plus plus state. To 0, 1 takes me to how do I call that? Is that minus I, or what is the deal here? So this is I, this is minus I, but it's not minus as in like it has a minus face. That's an important nuance in here. So this takes me to the. This is where I have to start using cats, I think, to just make sure that in the sense this is just a label. Minus I minus now the 1, 0 and the 1, 1. So so the 1, 0 is the 1, 1 is I minus, and I think this will be minus plus. Interesting. Minus plus. Okay, but what does this mean? So, and I think I flipped them in terms of zeros and ones, right? This is basically a superposition of 0 plus 1 plus 2 plus 3. That's what this is, right? Yeah, but there's gotta be a reason, or there's gotta be a way. Yeah, that's all fine. That's why there's nothing no, I mean you do, yeah, get a lot of these. But there's nothing being kicked in here. But there's gonna be something kicked with the modular exponentiation. For this I need R. So this is A, so the exponent. This is 1, and then I need B and R because this is times B. So what if B is just 1? So I think I can just say B equals 1. And R, no, because this is always 1, so that's, okay, but maybe there's something, and R equals 2, like, kind of, like whatever. Okay, so now it's actually, so what is it that we're now trying to do? Let's see. So we're now trying to do modular exponentiation. So what we're doing is we have our uh, 0 plus 1 plus 2 plus 3 and the 1 state. And so what modular exponentiation will do here is, so what are the operations? So we will do 1 to the power of 0 mod 2, 1 to the power of 1 mod 2, 1 to the power of 2 mod 2, and 1 to the power of 3 mod 2. So these are, but this is all 1, so we end up with a non-entangled state. Yeah, so the inverse QFT of each of those ends up canceling, and because it's the QFT of these as a block, not of each of them separate. Because in the previous case it was the superposition, it was sort of the mixture of all the QFTs that you're seeing at the end, right? Interesting. What if we change B to B2, right? Nothing's changed either. Oh, because it's mod 2. So let's just say mod 10. Mod 2 big. Mod 4. No, mod. Okay. Yeah, I don't know. I might do another session of these because I think this is an interesting way to an interesting path to take the entanglement hypergraph idea too at some point. That we have an operation where we can just say, entanglement hypergraph for QDs, or just kind of group nodes into registers. Basically, just do it like that, and then just kind of be able to build these kind of operations in there natively. Would make a lot of sense as well. But I need to make sense of how does Craig get here, like any kind of phase kick. I'm sure this is not implemented. Like, we'll take a look at Quirk's code next time. Let's see how this is all mechanically implemented underneath. Because if I remember checking the code for these briefly, and it's actual code. It's not like a matrix multiplication or anything. So it's, there's actually ifs and else and stuff like that. So I don't know how this is implemented. Maybe these can shed some light into that. But so 2, 4. It's too big. Okay, just because it's 2 qubits, so the mod must be max 4 probably. 5 is already too big. Yeah. 4. But I don't see any. Okay, what if mod is 3? Oh, there you go. Okay. So that's what we're gonna do next time. That's now where it gets interesting. There's definitely something's happened here. Well, yeah, because now we have some of the elements that are the same, and so the entanglement is really, yeah. I have the feeling it's not about phase kickback. That's the point. But I know at the same time that I'm probably wrong. So I don't know. I don't know.